The broadcast is now starting. All attendees are in listen-only mode.
Hey, welcome everybody. Coffee with Caleffi, Bob Hot Rod Roar. Today our speaker is Kevin Freidt. He's a product manager for us at Caleffi. He's also worked with technical support. Very knowledgeable person and a heck of a nice guy. So he's going to be leading the presentation today. I'll be in the background to help also. So today will be a lot of the slides that you're going to see, a lot of the information that Kevin's presenting comes from issue number 15 that we did a year or so ago on separation and hydronic systems. So he'll note that as we go along in some of the slides. What do you got here, Kevin?
All right, you ready to get going?
All right, take it away.
Okay, so we've got Bob, this is Kevin, and we also have Mark Olson on the line too. So between the three of us, we're going to cover all these topics here. A lot of these are based on the questions that came in pre-webinar. So we want to talk about air, how to remove it, what type of products we use to do that. And we'll talk about vents and air separators and how they work. And a little detail about the difference between some of the separators that are available on the market. How many air vents do I need? That's a common question that comes in, so we'll cover that. Where do I locate the vents and air separators? And chilled water, we can't forget about chilled water. So we'll cover all these things. And remember, if you have any questions, type them in the comment area and we'll either answer them as we go through here or at the end. And if we run out of time, we will answer all your questions. So be sure to enter your comments. All right, let's get going. It's all air to begin with, right? It's air in hydronic systems is a given. It's the challenge is really minimizing the amount that's in the system to begin with and then getting rid of it once the system is up and running. And I mean, we can't overemphasize the importance of doing a good job in filling and purging, because the more we reduce the potential for noise and damage that the air can cause in systems. So very important. And Bob's April Coffee with Caleffi webinar is on this topic, so the timing is really good. It's just perfect. So one thing to remember is you need to have enough of a pump. You need to have a good fill pump and enough velocity to push all the air through the piping as you do the fill. And you need to have at least 2 feet per second. This is a velocity that is sort of the key speed at which an air bubble will be able to be pulled through the piping. For example, in a vertical pipe, if you have 2 feet per second, the air bubbles will be pulled along with the water. If you have less than that, the air bubble buoyancy will actually keep the bubble from being flushed through the piping. So that's something to be concerned with. So, and remember too that all the fill water and the makeup water will contain air. That's just a fact. It's part of the game. And another way that air can get into the systems after we've filled and we're running is in vacuum areas. So for example, a valve packing, if we draw a vacuum where we have a ball valve located like this picture here, if the packing is a little bit worn, you can pull air into the system through that. The same thing for circulator flanges, for example, if they're not quite sealed properly. And if you draw a negative pressure at an air vent and you don't have an anti-suction cap, we'll cover those in a few slides too, you can pull air in the system as well. And don't forget too that PEX tubing, if you don't have the type of tubing that has the barrier for oxygen, you can actually get oxygen in through the system, through the tubing. So why do we want to remove this air? Well, I think one of the more important reasons is heat transfer. Air is a really good insulator. In fact, it impedes the conveyance of heat. For example, a given volume of water can absorb about 3,500 times more heat than the same volume of air. And you can see this thermal diagram here indicates how that air pocket up there is going to be much cooler than down below where you just have water. Air is a problem for more than one reason, but primarily it makes noise and can annoy occupants. And the important thing to know is that once you get all the air out of a system, a good hydronic system that's air-free is silent. So speaking of air, another source of noise is cavitation. And cavitation is generated when dissolved gases are released. Now this is a topic, you know, with a training session all by itself, but let's touch on it briefly here. So this example illustrates how cavitation can occur in a valve, just for example. So the velocity of the fluid over here on the left, let's say that this velocity right here, when it approaches a smaller cross-sectional area, as in a valve, the velocity will decrease and the pressure will, the velocity will increase and the pressure will decrease. For example, let's say if this incoming pipe were a 1-inch copper pipe with 6 GPM flow, that's about 2.2 feet per second velocity. And if this valve opening right here were a 1/2 inch, that velocity would increase to 7.6 feet per second. So there's a pretty big change. And pressure is inversely proportional to velocity. So as the velocity goes up, the pressure goes down. And if the pressure at this small cross-sectional area right here falls below the vapor pressure of the fluid, then these microbubbles will form from the dissolved air. So we have dissolved air coming in, but those microbubbles will actually form because we're below the vapor pressure of the fluid. And then when this cross-sectional area increases as we exit the valve, these microbubbles will implode and they'll go back into solution, and that's called cavitation. So besides causing noise, cavitation causes serious damage to the piping walls and to everything else in its path. And that looks like this on a graph. So let's look at this light blue line. So here's our velocity as we come through. The velocity increases and then it peaks right here at the smallest cross-sectional area. And then that velocity drops again as we exit. So here's the inverse proportion, the pressure. This diagram shows the pressure going below the vapor pressure of that fluid, and that's why these bubbles form right here. The same thing can happen in the inlet side of a circulator. So those dissolved gases can again be released from the solution and create cavitation right in this area of a circulator because of the velocity and the low pressure. Now, if you have air in a circulator, okay, that's a problem too, because air is compressible and circulators really are designed to convey incompressible fluid. So not only does the potential exist for cavitation, which will destroy that impeller, but also you get that compressibility, so the performance is decreased. If you have a lot of air in a circulator, especially a vertical circulator, that's especially vulnerable to air pockets. And you can see here, in this diagram, there's a spring-loaded check valve built into the downstream side of the pump. If you get a lot of air in here, that air can build up under that spring-loaded check valve and actually cause a big air pocket in here, and that will cause that pump to stop turning. Large air pocket in there where the pump is located, not only is it just spinning, but those bushings will be dry too, and the bushings in circulators need to be wetted, at least in this type of circulator, for lubrication. So that can be a problem, and you can cause a lot of damage to the bushings if they're not wetted. All right, let's move on. Also, air in the system can cause problems with other products like balancing valves in the system. For example, here's a cutaway. If you can imagine that you had air inside of this balancing valve, your pressure taps might not be picking up the fluid directly, and that could cause a problem also. Another big issue, this is a significant problem, is corrosion. So if you have oxygen in contact with steel and cast iron, this is the result. Corrosion causes a lot of damage. You can see here this pump volute, you can see the corrosion inside of this mixing valve down below. Obviously that valve isn't going to work very well. And you can see corrosion in the pipe. And then on this expansion tank, because air is about 23% oxygen, that's what drives this corrosion. And chronic air problems can cause serious damage and eventual failure of components like this. Another product of corrosion is magnetite. Now, magnetite, here are some nice pictures showing that. It's a dark gray sludge, can cause a lot of damage. It's highly magnetic, as you can see here, and it can be a real problem for ECM pumps. We show here, see that pliers hanging from that ECM magnet on the right, and you can see the collection of that magnetite material on that rotor. And that material is sometimes also called boiler ink. It's black and almost looks, it sticks to your fingers too. So this is a product of corrosion and also caused by air. So what we're going to do here is throw out a poll question. So in your experience, what is the main cause of air-related problems in hydronic applications? And Woody's going to throw up the poll. So improper initial filling or flushing, leaky gaskets or seals, air vents and air separators not properly selected, or you don't have any major issues with air. So go ahead and make your choice. All right, so let's look at some forms of air in hydronic systems. A stationary pocket, the first thing we're going to talk about is an air pocket. Now this is going to form at any high point in the system. Here's an example of an air pocket that's on a high section of pipe. So you can find these high sections in heat emitters, heat exchangers, expansion tanks, whatever. You can form these bubbles, and as they join together, they'll form these large high pockets, okay? The other form of air is entrained bubbles. So entrained bubbles, like this picture shows here, can be carried along with the fluid. And as long as you have more than 2 feet per second, then those air bubbles will be carried along. Now, some of these are visible, like cloudy water. Like if you take a glass of water out of a faucet that has an aerator on there, you can see that cloudy look, and those are entrained air bubbles. And the really small ones, sometimes you can't even see those. And the third form is dissolved air. Now this is air that's actually dissolved in the fluid. It's not visible. It's called in solution. And let's talk about that a little bit. Okay, so here's an example. This diagram actually comes from our Discal literature, and let's talk about this a little bit. What it is an example of how dissolved air turns into microbubbles in a boiler heat exchanger. So looking at this red line here, let's start at this cold, or not cold, but cooler temperature in the water in the boiler. As that water gets close to the boundary layer of this combustion wall chamber, the temperature increases significantly. So what happens is these microbubbles are formed continuously on the surface that separates the water from the combustion chamber due to this high temperature. And these bubbles are carried from the boiler to the rest of the system by the flow of the water. So these bubbles will appear and disappear with changes in temperature and pressure. So they will go, from being dissolved to being microbubbles invisible, and back and forth based on the temperature and pressure of the fluid. Now these bubbles can be removed downstream by an air separator before they dissolve back into the fluid. So as those bubbles form, what we need to do is remove those from the fluid before they then get redissolved back into the fluid. Here's a graph that we like to use. This shows the water's ability to hold air. For example, let's say that we have a boiler system that's charged up to 15 psi, so that's this red line right here. And we have cold water, 65-degree water coming into that boiler. At 15 psi, that water, the properties of that water in terms of holding air are about 3.6% can be dissolved. In other words, if you had 100 gallons of water, 3.6 gallons of that would be air. Now, as we heat that water up, we come down this red line right here. We drop down this red line. When that water reaches 170 degrees, the property drops to about 1.8, which is half. So then in that 100 gallons of water, about 1.8 gallons of it are air. So what happened to the rest of that air? Well, it went from dissolved into microbubbles and then became, you know, bubbles, so we could physically pull those out of the system. Does that make sense? Now, what about if we have chemicals or additives or glycol? What changes? What things happen here? Well, first of all the fluid properties change. So the density, the viscosity, the boiling point, and these properties change. So as a result, the air vents and separators will still work, but the efficiency can change. In other words, it might be harder to remove that air because we have different properties of the fluid. And because there's oxygen and air in the system, we know that that degrades glycol. In other words, it breaks down the glycol. So it's even more important to make sure that we have effective air removal when we have additives and chemicals. Let's talk about devices that are used to remove the air. So high point air vents are one, and you can see a bunch of pictures here that show where air vents are located. For example, at any high point in the piping, as shown here, on the top of a solar collector array, on the top of a hydraulic separator, manifolds, and other locations. So again, here's the high points that we were talking about. The other device used to remove air are central air separators, and we'll talk about those too, both in heating and chilled water systems. All right, let's start off talking about air vents. So manual air vents, like shown here, they're usually small. They come in 1/8 or 1/4 inch sizes, and here are a couple of pictures. This is a little cutaway of our 337. And here's an example of that installed in the side of a radiator. So what you do basically is just open it until water flows, and then you close it. It's just a little manual valve. Here are a couple of other illustrations that show it being mounted on the side of a radiator and actually on the top of a baseboard T. Okay, hygroscopic. Now this is a really cool product. It's an air vent that is manual, but it's also automatic. Let's talk about that a little bit. What it has inside are these natural cellulose fiber washers that will expand when they get wet. So if you look at this cutaway, if you unscrew this top, you can actually open this inside here to do a manual vent, but normally you keep these closed. And when this is screwed closed, those O-rings form a seal right here. So this air is allowed to escape up through these fibers and then out the vent underneath the cap up here. So if they get wet, what happens? You can see here on the right, the certain thickness of the disc when it's dry. And as soon as it gets wet, it just within a few seconds, it expands. And what that does is it closes off that air escape and prevents water from getting out past your vent and dripping on a ceiling tile or something else that might be sensitive. And here's a picture of our 5080. That's a chrome-plated hygroscopic air vent that Caleffi sells. Okay, let's talk about an automatic air vent. Here's a cutaway, which is really nice. It shows the float inside, and you can, I don't know if you can see the water level here, but what happens is as air builds up inside of the body of the vent, this air gap on the top increases in size, and so the float will drop, and at some point it's going to drop enough so that this little linkage right here is going to pull down on this needle valve to let the air vent out through the vent cap. So this float just moves up and down to open and close this little tiny needle valve right here and let the air out. That's the fundamental function of an automatic float type air vent. Here's a cap. Now, the air vents that we sell are available with the hygroscopic cap that I just talked about. So those are options. You can, if you get an air vent that just has a plastic cap like this, you can put a hygroscopic cap on there if you want to. And then down below, we have something called a service check valve. Now, we offer models that have this, or you can buy it separately. And what that device is it screws on the bottom of the air vent, and it allows you to remove the air vent if you have to service it for some reason, and that little spring-loaded stop on the bottom closes, so you don't have to, open a valve in the system or anything. That's like a little, it's like a Schrader valve type of spring-loaded valve that will close if you need to remove the vent. This cap right here is called an anti-suction vent cap. So you can replace the vent with this device, and what it will do is let air out but not allow air in. So if you have an installation where you're having problems with pulling a vacuum at the location where the vent is, you can put that cap on there and that will solve that problem for you. Here's another version of our vent. This is called a Discal Air, and this one's a little fancier. It has a pinned float. So functionality is very similar to the one on the left, but this one has a pinned float which guides that float and keeps it from maybe rubbing up against the sides of the inside of the vent if your vent isn't perfectly vertical. And that's a stainless steel pin. It's a little higher capacity, a little more of, like I said, a sort of a fancier vent. That's called the Discal Air. And then we have our big commercial models here. That's what the cutaway looks like. It has a large stainless steel float and, similar functionality. It's a little more complex inside. It has a very high capacity to relieve air, but functionally it's very similar. And here's what the family looked like. That little one on the left is called our compact air vent. That's got 1/8 inch connections. And then we have the next group, our mini cal. You can see the one on the top has the black plastic cap, and the one on the bottom, there's that hygroscopic cap. That's what that looks like. And then we move into some larger sizes. Again, the Discal Air, and then on the far right, that big commercial high volume vent. Moving on, let's look at, this is a great picture. I like this for a couple of different reasons. Here are 3 boilers installed. Now up above, look at, I know it's hard to see, but you can see the air vents in these little red circles, but what's on top of those is a piece of copper tubing. Now what this contractor has done is put a discharge tube on top of these air vents, and we make a little adapter that you can screw on where the vent cap goes, and it takes you to a 1/4 inch NPT. So from there you can put a compression fitting or some kind of a discharge tube. That's in case these valves, these air vents do get a little debris or get clogged up for any reason, and they start to spit water, then you won't drip on top of the boiler and cause any damage. So just want everybody to know that that's pretty common practice, especially when you're located somewhere like this right on top of the boiler. And then over here on the right, there's, it's a little hard to see, I know, but that's our commercial air vent, and the customer's done the same thing here. He's attached a discharge tube to the top of it. So great installation up in Surrey from Rocky Point Engineering. All right, let's summarize air vents. Okay, there are a few things really to take away from this. Make sure you design your system so that you always have at least 5 PSI at the highest point of the system. We want to make sure that the vents will always expel air. We don't want to draw a vacuum up there or anywhere where you locate a vent. We want to make sure that the discharge pressure rating, now this is a spec item, make sure that the vent you're picking or selecting has a rating, a discharge pressure rating greater than what you will see in your system, because if the system pressure is higher than the discharge pressure rating, what happens is the little needle valve will be held closed so that no air will escape from the system. So just make sure you check that. Again, avoid a vacuum. We've been talking about this, but if you put the expansion tank in the wrong location relative to the circulator, you can draw a vacuum. Now, I would suggest if anybody wants to see how this works, look at Hydronic's pages 35 and 36. There's a really good explanation there in our Hydronics journal on what that looks like. So you want to make sure and locate the tank near the circulator inlet. Install the vent as vertical as possible. Again, like the reasons we talked about, if it's off a little bit, that float might ride up and down on the side, the inside wall of the vent, and over time that can stick or maybe not work as well as it should. And again, locate the vents at all your high points. You may need 4, 5, 6 vents, depending on your piping. We get that question a lot. How many vents do I need? Well, how many high points do you have? That's the point. And be sure to locate them for serviceability. It's very possible that over time you can get some debris or buildup up in that little needle valve. It's a small orifice, and you may have to take it apart and clean it. And by the way, the vents are easily cleaned. You can unscrew the top, take them apart, clean them out, put them back together. They'll be as good as new. So if one starts to weep or drip, that doesn't mean you have to replace it. Probably just needs a good cleaning. Okay, let's move to air separators. A purger is a type of central air separator that's semi-effective in removing larger bubbles, only at low velocities though, and it does not remove microbubbles. So it relies on the buoyancy of the bubbles to actually remove the air. And what did you say, Bob? It's like the rotary phone of central air separators. It's kind of outdated, but we still see them out there.
Yeah, the main thing on that one, Kevin, is that, you know, the intention of that device is they make a big wide spot in the road. So as the flow comes into that, it slows down for a second as it goes through there, reduces the velocity, trying to encourage those bubbles to go up to the top and find their way out of that little, typically 1/8-inch air vent on the top. But yeah, those little micro bubbles and trained air, it just doesn't have any mechanism that Kevin's going to explain on the next slide to grab those and capture them and float them up and release them. So in its day, it had a place, but there's a better way to do this now, especially with high efficiency equipment, both boilers and heat emitters.
Right. So central air separators, they have a coalescing element that captures microbubbles. So here's a graphic that sort of illustrates that. As the flow comes in through that pipe, you can see at the bottom, these are really small bubbles, and what those little bubbles will cling to the sharp edges of a coalescing element, and the bubbles will join together and rise up as their buoyancy increases and eventually become large enough bubbles that they'll go up to the top, and then they'll build up in the top of the air vent and be expelled out of the system. So again, the key is this coalescing element down here. Now, what helps this whole process is that when you come into an air separator, you have basically a large barrel. Okay, it creates a low pressure, low velocity zone, and that zone where the water slows down promotes the coalescing of the bubbles on the element and the buoyancy. So again, an air separator is not a filter, so they don't have much of a pressure drop. I'm going to talk about that in a minute, if at all. And so they don't typically require service. They just do their job. If we look at a cutaway, here's what that might look like. As your flow comes in with the entrained air, the coalescing element is in that flow path. You can see the increase in cross-sectional area there where the water slows down and those bubbles coalesce and then bubble up into the air vent and then get discharge out of the cap. So that's a nice cutaway that illustrates how that works. We get the question on what size of an air separator to pick. I think this is one of the pre-submitted questions actually. What we suggest is that 4 feet per second or less is ideal. And you can go up to 10 feet per second in velocity, especially in your larger flanged units, because those are big pipes, and even in chilled water systems, for example, we tend to have higher velocities. So up to 10 feet per second is still okay. You'll still get air removal, and the coalescing elements will still scrub out that air at that velocity, at least in our products. That's what we say. Now, I mentioned low pressure drop. Typically, that's a negligible thing. So when you're doing your head loss calculations in your piping, you don't need to count these. You don't need to count an air separator. If you want to, you can look in the literature that we offer. There is a flow versus pressure loss graph in our literature, but it's a really, really small number. So check that out if you want to. But again, typically we say you don't have to worry about it. Another question that has come in is, are there requirements for straight pipe lengths, upstream or downstream of an air separator? And the answer is no. They don't require that. Straight pipe lengths are typically applied when you are measuring flow, like in a flow meter or a differential pressure sensor of some type, but this device doesn't need that. Here's a nice cutaway of our commercial model. Now you can see the coalescing element in there. And what you'll notice too is on this one, the air vent has a really long float chamber. And what that does is it prevents debris from getting into the vent mechanism. And the picture on the left shows you how you can pull the whole thing out and clean it. If you do need to clean it for some reason, if you have really bad water, the whole thing comes apart. So you can get in there and service it. And this thing right here on the side is called a side drain vent. And what that is for is you can open that to release large amounts of air when you're filling the system. So you don't have to wait for the little air vent to purge out the air when you're doing your fill. Just open that valve and let that air come out quickly during the fill. Also, you can use that and open that during the life of the system to skim off any impurities that might be floating at the top of the water level. So that's another purpose for that side drain vent. Here's a graph that comes up a lot. Okay, we get a lot of questions. What's the efficiency, or what is the specification for your air separators? And this is an actual test graph. This is based on empirical data from testing we did at one of our labs. And what we did, this blue line here, you can see we introduced a certain amount of air within 10 seconds. Okay, on the bottom here, or is that 7.5? No, that's 10 seconds. So we introduced some air, and then we measured with a mass flow meter the air being removed as it was introduced. And you can see immediately it starts to remove the air. And then over time, the x-axis down here is time. So after about 1 minute, we're already at 96% of the air removed. And as time goes on, that red line just continues to get more and more close to 100. So the point of this graph is that, air separators are multi-pass devices and they take time. So this illustrates that pretty clearly, I think. In this testing we did, we compared a lot of different products on the market, and here are some images of the 5 brands that we tested. And it really comes down to all the popular air separators that are available and that are successful on the market have some type of coalescing media that you can see here. And they all will allow bubbles to cling to the edges of that media, and over time and over a number of passes, that air is removed. Now, depending on the coalescing element, some may be faster than others. Some may be more stand up to chemicals and impurities better than others. That top one in the center is ours. It's a type of non-metallic product, and that really holds up to chemicals if there's chemicals in the water. And another thing to mention here too is there's no standard for air removal performance. So we do get the question, what about your efficiency? Whose is better? Whose is faster? Whose does a better job? Well, it's honestly it's a lot of specsmanship, because if there's no standard, anybody can make a test that has results that may be favorable. So the point here is that they all remove air over time, and we know that ours gets up to that 100% mark over time as well. And I should also mention there's another type of technology called a tangential or a vortex air separator out there. Now, Caleffi doesn't make these, so I don't have a lot of detail about them. I'm not an expert, but I do know that they're based on a cyclone principle. And at the center of that cyclone is a low pressure zone. So what happens is those bubbles will rise at the center of that product as the cyclone or the vortex forms. And this is a simple, sort of an older design. It's been around for a long time. But something to think about or to know is that these are dependent on pressure and velocity. So if you have, for example, a very low velocity, you may not get a very good vortex. And if you don't have a good vortex, then you're not going to have very effective air removal.
Hey, Kevin, can you hear me? This is Mark.
Yeah, Mark.
Yeah, on this type of separator, it's important on that velocity, as you mentioned, because you want to basically, you're basically relying on the velocity to send the air bubbles towards the middle and then up out the vent. And A problem with these is basically sizing these based on pipe size. So what that means is that if your pipe has been sized to deliver 4 feet per second, and you basically sized your separator to be equivalent to that, I mean, to match that pipe size, it might be insufficient velocity going around that vortex to create the action needed to get rid of the air bubbles. So that's one of the issues with this type of product.
Right. And what if you put in a variable speed pump and this pump slows down? Then you're going to be looking at the same potential problem.
Right. Correct.
Right. So like I said, we don't make those, but we make these. So here is the family of our air separators, starting from that small compact unit you can see there. By the way, I show also that service valve down here. That same service valve is can be used on the bottom of an air separator, and a lot of installations use that bottom connection on our air separator for their fill and flush connection, and also for the expansion tank. Very common use. So that compact one, we have the disc gal shown with the press connections up to 2-inch in brass, and then we go into the larger steel ones. And you can see the steel ones have, again, they have that side vent tube. Okay. These steel products have ANSI 150 flanges. All of our steel vessels have ANSI 150 flanges, and we have ASME and CRN for our Canadian friends, all the way up to 8-inch. And we can go larger. It's just a matter of money and paperwork, right, Mark?
So to speak.
Okay, let's talk about where they are placed. Okay, because of what we talked about with pressure and temperature and removing microbubbles, we want to locate an air separator where the temperature is high and the pressure is low. So here are a couple of pictures of our schematics showing a horizontal and a vertical air separator located in the hot supply line from a ModCon boiler. And you saw this before too. On a chiller, we're going to put that in the warmest pipe, which is leading back to the chiller.
Hey, Kevin,
Yes.
Going back up to that last one, a question came in. Is the air separator placed directly after a boiler always the best location? And as you show it here, directly after the boiler. And in many cases that's true, but we have to remember the pressure effect on air coming out of solution. So let's say, for example, take that boiler in the middle. Let's say we're running, let's say our zones are a couple of stories up, 2 or 3 stories up, for example, before we start zoning branching off. Now, as that water has traveled up, albeit at pretty much the same temperature as coming off the boiler, that reduced pressure as you go up the building is going to release more air that you otherwise wouldn't have captured with the separator placed exactly there. So it's the answer is dependent on your application. And so by way of what I just mentioned, by placing it up close to where you're starting to zone off, then that would give you the advantage of both A, high temperature, and B, low pressure, which is the place you're trying to look for when putting the proper placement for an air separator, or I should say optimal.
Yep, exactly. Good point. And remember, it's you know, if it's really difficult to locate it in one place, you can locate it in another place. Just try and follow the high temperature, low pressure rule as best you can. And remember, they're multi-pass devices, right? So maybe it'll take a little longer. If it's not in the absolutely perfect location, you'll still get effective air removal.
Hey, Kevin, another question came in here on this particular slide. Before you leave, sorry about that.
Yeah, no
on the
problem.
chiller application, there we don't show an expansion tank. Now, ideally, you're going to have an expansion tank on a chilled water system, just as you would a heating system. And as you would in a heating system, you always have your expansion tank placed upstream from your pump. You want to pump away from your expansion tank no matter what. So you would put it on the suction side as you would on the heating side.
Okay, good. Great questions. Okay, another schematic, just a variation here. This is a geothermal heat pump. So right in the middle, here we can see a good location for an air separator, right coming out of the buffer tank. also in the same supply line here. This one's perfect because it's on the suction side of the pump, so that's a great location for this one. And then of course, as we have heating zones, if we have any high points out in that piping, you want to put air vents out there too. Another picture just for variety. Here's a conventional boiler, so we show the air separator right on the outlet, and this is a boiler protection valve, so that's for here. But what I wanted to show too is, remember, here's some high points out here. So our manifolds will want to have air vents out on any high point location out there too. And a mod con. This is a nice picture. I like it because here's a vertical air separator. We have closely spaced T's, which is really common, and we have a primary circulator here. So this circulator is pumping water in this loop right here, and we show a dirt separator down here, a magnetic dirt separator. That's another webinar. But again, we have air separation here, and then we're going to have air venting out here at any other high points. So I'm thinking you're getting the message by now. Here's a couple of projects, the pictures that came in. By the way, we love pictures. Please send pictures. Here's an illustration of closely spaced T's and a nice disc gal location right here. Great job. Here's a picture of a disc gal that has the insulation jacket. Now we make these preformed insulation jackets like we show here. And this one even has, as I mentioned earlier, the bottom connection. You can see this small tube is coming out here, and this is a fill valve. So here's a backflow preventer and an auto fill valve. Then when the system gets finished, that will be the location of the fill for that. Thanks for that picture, Ashley. Here's another picture I like. Here is a disc gal, again, with the, now here's the expansion tank and a valve hooked right to the bottom. So here's the filling location. Again, another magnetic dirt separator and a good picture of some air vents up on a manifold assembly. I like this commercial example here from EMCO up in Quebec. Here's a flanged version, and again, look, the bottom connection here is hooked to a fill valve. Now this is a 3/4 inch. It's a slightly larger commercial size fill valve with the backflow preventer here as well. This job isn't finished, but nice shot of a flanged disc gal. Caleffi also makes air and dirt separators. So this is a combo unit. The picture we're showing here is called a disc gal dirt mag. And if you look at the upper half, this top half of the disc gal dirt, it's an air separator. Everything is the same from here up. And what we've done is added dirt separation in the same housing. So this is a 2-in-1. This particular one has magnetic dirt removal and dirt removal down here and a purge valve on the bottom. So where do we locate that? Well, we're showing it in this schematic, again, in the hot pipe right here. Now, we get that question, well, if I have a combo unit, do I put it here where the temperature is the highest, or maybe I should put it back here on the return to the boiler so I eliminate the dirt before it gets into the boiler? Well, it's our general opinion that that the temperature trumps the dirt removal. Why? The air, it's extremely important to get the air out for reasons of corrosion and everything else that happens downstream. Now, we'll pull the dirt out right here, that's true, but that dirt has already passed through here. But if it were me, if I had to make the call, I would say that, put it on the high temperature pipe. Here's what the air plus dirt separators look like on the inside on the commercial models. So here, again, we have the lower housing, right, doing the dirt removal, and the upper section with the long stroke air vent and the side port and this coalescing media, filling up the whole entire section of the body. This one on the right just happens to be an image of the magnetic, the Na546M with magnet. So this has magnetic, air removal, and dirt removal all in one device. Here are a couple of installed shots. The one on the right is a really nice picture. You can see how it's installed with the flanges, the mating flanges, and here's the flush valve down here. It's got a nice valve garden hose type connection on the bottom. This one over here has the magnet. If you look close, you can see this magnetic handle that screws in, and the magnet is up inside the body in a dry well. That's a nice shot from Abby Frum.
Hey, Kevin.
Now take the, yes.
You want to go, Kev, you want to go back up to that one? Some questions have come in relative to, we've been talking about air separators, but should a dirt separator be used also where you have an air separator in a system? I mean, when do you use a dirt separator? And do you want to take a shot at that, or you want me to respond? Or
sure. Well, you know, maybe from a purist standpoint, you'd want to put an air separator up on the hot supply pipe and put a dirt separator on the return to the boiler, especially, you know, if you have a high efficiency boiler that's very sensitive to dirt, that might be, you know, the ultimate way to go, because then you're scrubbing out that dirt before it gets into the small passages and sensitive areas in a high efficiency boiler. But a lot of times it's just that's inconvenient. It costs a little more to have two devices, and so often using a two-in-one like we show here, of course it's going to reduce labor. It's only 2 connections instead of 4, and maybe the project just doesn't have the room or the budget for separate devices. So that's my take on it. I don't know if you or Bob have any other comments.
Yeah, I got a couple thoughts. Since we got looks like we got a little bit of time here, I can see where you're at in your slide. One thing I was thinking about, if you're doing a brand new system and it's got all brand new copper pipe, maybe PEX tubing, brand new boiler, brand new pumps and stuff like that, I think the more critical application is to get the air at the hottest point in the system, which would obviously be the supply right out of the boiler. Now keep in mind, if a boiler's running at a 20 or 15 degree delta T, you don't have a huge temperature difference between your supply and return. Now the other school of thought is if you're connecting a new boiler to an old system that's got maybe iron pipe or cast iron radiators in it, or steel piping that has rust and debris in it that is going to continue to flake off as that system goes on with the new boiler installed in there, maybe the better position is on the return, because I'm concerned about, you know, catching that that sediment and dirt that's going to come out of that system for probably the rest of its life. So that might be one way that you look at it. You know, if you've got a two-in-one device here, what's going to be the best bang for the buck on the particular application that you're putting into it? Because again, the temperature coming back to that system, if it's running a 15 or 20 degree delta T, isn't that much cooler than it is right at the outlet of the boiler. So that might be something else that helps guide you in decision. But we offer all the options. You know, if you want to put an air separator on the hottest point, a dirt separator. Certainly with a magnetic device, I would encourage everybody to consider the magnetic device if you're using the ECM technology, which I think Kevin's getting to next. I think that's coming up, but that might be another determination on which device to use and also where to put it.
Yeah. So we're going to go from air plus dirt now to what we call our SEP4. This is air plus dirt plus hydraulic, and it has magnetic separation. So this device is a 4-in-1, and what it's doing is separating the primary circuit here with our ModCon boiler from the secondary circuit serving our zones. Now what we have here is this upper section. Again, there is our air separator. The coalescing media right inside here is scrubbing out the air, and the air vent is releasing it to atmosphere. Down below we have the dirt separation. We have a coalescing element down here as well. I'll show you what that looks like. That's scrubbing out the dirt. So we have the magnet on this small one. The magnet is a collar. It's a snap-on collar, and we have the dirt coalescing going on down here, and the air coalescing going on up here. So again, a very efficient product, right? With 4 connections, you get everything you need with hydraulic, air, and dirt, plus the added benefit of magnetic. And again, we still have our vents, right? We always have our high point vents. Sorry, Bob, what was that?
Yeah, one other point on this too. The dotted line on the top of the SEP4 there is what we're showing there is we also give you a little convenience well there, or convenience port, that you can put a sensor well in there. And so what a lot of installers will do is they'll take the operating sensor out of the boiler and stick it into the hydraulic separator. So now look what you're doing there is you're turning that boiler and that separator into a miniature buffer tank for your system. So in addition to the fluid volume in the boiler. Let's say that boiler holds 2 gallons of water. My separator may be 1.82 gallons of water in there, plus all the piping. So now that entire circuit there from the boiler through the separator back up to the boiler is now additional fluid capacity for a miniature buffer thing. And also what that will do is when you do have a call for heat on that ECM pump that we're showing off to the right there, that whole circuit is already warm because the boiler is keeping itself warm, keeping the separator and the pipe excuse me, to and from the separator warm. And so we see a lot of installers like to use that port that we give you there. And we also have a well that you can screw right in that port that'll take a typical 6mm sensor that most of the boilers are using now in their controls. So that gives you, I guess you could call it step 5 if you consider that as a another function of that device.
Yeah, I like that. So these products, again, we have a full range. So that one we showed on the earlier slide was this small one on the left with the union connections, and that comes in sweat, threaded, or press. So the tail pieces, you have good flexibility there. It comes with that insulation jacket with the top and bottom piece and the front piece to cover it all up. And then the one in the middle, the 2-inch to 4-inch, those also come with pre-molded insulation jackets. And you can see a picture here. This one shows the magnet is the insertion type. So this has the dry well that goes up in the return flow path in this part of the device where we're scrubbing out the dirt. And that has a commercial size air vent on the top of it as well. And then these great big ones on up to 14 inches, they have legs. And this picture actually shows one magnet, but there's actually 3. These really large ones have 3 insertion magnets on the bottom. And again, here's a location for a sensor and our commercial size air vent up on top. So that sums up the step 4. So let's wrap it up. Let's kind of bring it all together here. Of course, effective air removal is critical. I think we've pretty much driven that home, right? It's very important for a number of reasons. So it all starts with proper filling and flushing and purging. And we need to minimize that air at the beginning. If we don't, we have more problems down the road. So let's get that filling and flushing done properly to begin with. Locate the air vents at high points and locate your microbubble air separators where you can, based on everything we've talked about with pressure and temperature. And remember, they're multi-pass devices, so they will get rid of the air. And if you do all these things, you'll maximize system efficiency, your customers will be happy, and you'll extend the longevity of your equipment. Of course, that's the goal. So if you get the air out, this all can be achieved. And I hope we got all that information across. And that's about it. I think we have a couple of minutes. If we have any questions, Mark, we can answer a few questions. But again, everybody, make sure that if you do have a question, send it in. I will personally respond to it, Bob or me, and we'll get back to you. But if you have any right now, Mark, do we have anything that we can talk about before we let everybody go?
Yeah, okay, a couple of questions, a lot of questions, but we've been answering as we go here. One of the things that is sometimes done, Kevin, that on air vents, if you look into the top of an air vent, sometimes you'll see what looks like a Schrader valve, or basically a little needle that you can depress there. And by doing that, what happens is that if the air vent is under pressure, it releases all of the air that's underneath that air vent and providing a kind of a cushion from any debris from getting up into the needle valve that is crucial for preventing any type of weeping. So unless you absolutely have to, we don't recommend taking an air vent when a system is in service and depressing that valve. There really is little need to do so. And it just increases the chances that a little bit of debris can get in there and cause a weeping. All right, and that's some folks just in general like to run a pipe, as you showed in one of those earlier slides, from the top of the air vent over to some place in case there is a little bit of weepage, so that the moisture gets drained off somewhere it's meant to be. And another question, there's some questions on glycol again, concerning glycol and air separation. Yes, anytime you put glycol in a system, what it's going to do is it's going to cause the efficiency of removing air out of the system lowered. And the reason for that is glycol has a higher boiling temperature than water. Glycol will boil at, I guess, 380, and water, what, 212 at atmosphere. And so if you have a 50-50 mixture of glycol, which is not uncommon in Canada and parts of the United States, your boiling temperature is going to be somewhere 290 degrees Fahrenheit. And you showed that chart of the boiler wall with the flame temperature and the water temperature. And you can see that just looking at that, when you have a glycol system, all things being the same, it's more difficult to cause air to come out of solution so that you can grab it and for the air separator to do its job, coalesce and get rid of the air. It wants, if it does boil, it wants to go back into solution quick. So as a result, it's very important to have a high efficiency air separator, which means if you have a glycol system, you should be looking at coalescing for sure, and make sure you have optimal placement of that separator so that you can quickly get as much oxygen air out of solution. Also, glycol is very viscous compared to water, and it prevents the bubbles from wanting to migrate up as quickly as they would in air. And as a result, they have a higher tendency to carry through a separator. And resultingly, it's they spend more time, oxygen will spend more time in a glycol system. And of course, glycol it scavenges oxygen, and as a result, that's why glycol manufacturers will typically include an inhibitor with their glycol. So probably more than was needed to know, but I just wanted to explain that because there was 3 or 4 questions that came in on that.
Yeah, good point.
I think a good bottom line to that, Mark, and everything you said was excellent, is just it takes more time to get air out of glycol. I mean, a discal, you put it on the system, and by the end of the job, at the end of the day, you've got all the air out. It's 100% air-free and quiet. It could take a couple days to get it out of the glycol, certainly raising the temperature and that fluid's just a tricky fluid for a lot of different reasons. Number one, getting glycol tends to leak out of a lot of threaded connections and stuff. It's the only good thing about it is it doesn't freeze, I suppose.
Now, another question came in. It was on expansion tanks, Kevin. I guess we were trying to chime in there, but expansion tanks, we had a listener that has expansion tanks that corrode out, and I think you showed an example of one of the ones that we had in our lab that corroded. And when it's especially important, some contractors will take an expansion tank and mount them upside down with the expansion tank above the pipe. And if you think about how an expansion tank is designed, air can get trapped up underneath the bladder there and come in contact with the inside of that expansion tank, which in many cases is just steel. And unlike a riser, top of a riser where air also can get trapped, but where you can easily put an air vent and expel any air that gets trapped, you can't do that with an expansion tank. And as a result, it's a good place for air to want to get trapped and stay trapped, and only to react with its surroundings, being the expansion tank. And the telltale sign is that blister on the paint that tells you that your expansion tank is just about ready to corrode out. So proper orientation of the expansion tank is for good design is important as well.
Okay, well, if that's it, I want to thank everybody for listening and hanging in there. We've still got a lot of people hanging in, but again, send your questions in. We're here for you. Let us know if you have any questions. And that's a wrap. Thanks very much, Bob. Thanks, Mark. Goodbye, everybody.